Today our speakers are Megha Hebbal, who is currently doing BSc in Mathematics and Computers from St. Joseph's University, Bangalore, and we also got our speaker as uh, Manogna Mysuru, who is also doing BSc in Mathematics honors from MS Ramaya University of Applied Science in Bangalore. Over to you guys.
Thank you for that introduction.
Okay, so today we'll be presenting about Lagrange's interpolation polynomial using linear algebra. Myself, Manogna, and Megha will also be presenting this. So first of all, we've all viewed animation films, right? In those, how do they actually produce a film like that? So the thing is, they write uh, diagrams and drawings, and then they merge it so smoothly that it becomes a movie. So how do they merge it so smoothly? And there's another example, that is census. They don't take the population of every year, but they take only in the gap of 10 or 5 years. And what do we do to get approximate population of non-census years? What do we use to get the number or data? And how's the weather up there is to say that when predicting the weather of certain regions where you can't actually go and get direct observations, you take the certain datas of heat, wind, temperature, etc., and you calculate five of the nearby observation areas, and then you finally conclude that this might be the weather in a particular region when you can't access that particular region. So, in all these applications, we use Lagrange's interpolation polynomial. So,
So the
this is
thing is,
all complex.
yeah, and so the thing is, all of those concepts are very complex, right? We don't, and they take into account a lot of factors, which right now is out of our scope. So let's just start with what we know. We know we are comfortable with the 2D space. So say we have 2 points, right? Just let me know if you're able to see when I write here. Is this visible?
Yeah, yeah.
Okay. So right now, say we have 2 points in R2. How would we join these 2 points? Like with which polynomial would we usually join these 2 points? A straight line, right? Forgive my drawing skills, they're not very satisfactory, but this is what we have to work with. So say we have 3 points now. How do we join these 3 points? Usually with a quadratic polynomial, which looks something like this, right? And say we have 4 points. 1, 2, 3, and 4. How do we join these? So we'll have something like this. Imagine it's passing through those points, but yeah. So now this is a cubic polynomial. So here, in this case, we can also use a quadratic polynomial that passes these through these 2 points. It should look something like this, or it might look something like this, right? But say we want the smallest degree, that would be a straight line. Similarly, here we could also use cubic polynomial, right? But then, for simplicity's sake, we don't want to overcomplicate things, so we just use the most minimum degree that we can work with. And in general, this is we've looked at 2 points that uses 1 degree polynomial, 3 points that uses 2 degrees, a polynomial of degree 2, and 4 points that uses a polynomial of degree 3. But now, say we want in general, how do we come up with a polynomial having, and in our hands, say we have n points, how do we come up with a polynomial of degree n minus 1, right? And that is where our Lagrange's interpolation formula comes into the picture. So the theorem states is stated as this: let n be greater than or equal to 1, and let's say we have n points x1, y1, x2, y2 till xn, yn, and all of these points are in R2, such that x1, x2 till xn they are all distinct. Now there exists a unique polynomial f that belongs to Rn of x. This is nothing but the notation for the polynomial space whose degree is at most n, of degree less than or equal to n minus 1, such that the curve y is equal to f of x passes through all the endpoints. So in other words, we have yj is equal to f of xj for all j is equal to 1 till n. And furthermore, the formula is given by this. Now, this might look very daunting and scary, but let me just break down this formula for you and how it looks. So here we have f of x. This f of x should be equal to, now let's go term by term, right? So the j over here goes from 1 to n. So the denominator will look something like this. So we take j is equal to 1 and we have x1 minus, and in the denominator we skip all the coordinates where k is equal to j. So we don't use x1 again, we use x2. x1 minus x2 into x1 minus x3, so on until x1 minus xn. This is in the denominator. In the numerator, we do x minus x1, right? Yeah. Sorry. This should be x2, x3, so on until x minus xn, and then here we multiply it with yj, or here y1, right? And again, this is just the first term of that polynomial. Second term, we do the same thing. In the numerator, we skip that jth term. So x minus x1, we skip x2, so x minus x3, so on until x minus xn, right? And then in the denominator, we use the skipped term, which is x2 minus x1, then again x2 minus x3, so on until x2 minus xn. And you multiply this whole thing by y2. So on and so forth until you reach the last term. So this is how our interpolating formula actually looks like. And Manogna will take you through the proof now.
So going on with the proof, first we'll take the most basic case, that is considering all y coordinates, that y1, y2, so on up to yn is 0. Then it is obvious that the polynomial will be 0 polynomial. Going on to the next general case, where we consider one of the points to be 1 and all other points to be 0. Here we are considering y1 to be 1, that is f of x1 should be 1 and f of x2 to f of xn will be zeros. Then we also know that for a function to have roots, the root, when you put it into the function, you'll get the value 0. So they are all zeros of the function, right? So from that, you can find the factors of the function. So here, since x2 till xn are giving the function value as 0, they're all roots of the function f. So I can consider that the factors of this function is x minus x2, x minus x3, so on up to x minus xn are like factors of this function. So the function will look like q of x into x minus x2 till x minus xn. Q of x is the leftover part of the polynomial. So how do we calculate q of x? For that, we also know that the polynomial will have degree less than or equal to n minus 1. So here we are considering it to be equal to n minus 1. So x1 minus x2 to x minus xn are n minus 1 terms, which will clearly say that the polynomial is n minus 1 degree. So from this we can conclude that q of x must be a constant. So from the extra fact that we already know that f of x 1 is 1, we substitute x1 in all these data points x, and we find the value of c as c is equal to 1 by x1 minus x2, so on up to x1 minus xn. Therefore, we substitute the value of this c in the interpolating, our first interpolating polynomial, which looks like f1 of x is equal to x minus x2 to x minus xn by x1 minus x2 to x1 minus xn. This is the first term we also saw when Megha was writing. So f1 here says that the first data point, that is y1, is equal to 1, and all other data points y2 to yn are 0. So this is the first general case. So now, what if we take yj as equal to 1 and all other yks where k and j are not equal are 0? Then where j is ranging from 1 to n, so j can be anywhere in between and all others are 0. Then for this, we are going to generalize it and write it. Megha will write it for you.
Yeah. So this fj of x basically tells us, it basically denotes a polynomial which has fj of xj should be equal to 1, and fj of xk will be equal to 0 when k is not equal to j, which basically means that this polynomial fj will vanish at every other data point, at every other xk, when and only at xj will it be equal to 1. So it will look something like this. So in the numerator, we again omit the jth term, which means we'll have x minus x1 so on until x minus x j minus 1, and then we'll have x minus x j plus 1 until x minus x minus xn. Because of lack of space, I'm not going to write that. In the denominator, we take the omitted term, which is xj, right? And then we subtract x1, so on until xj minus xj minus 1, and then we skip the jth part, otherwise this will become undefined, right? So xj minus xj plus 1, so on until xj minus xn. So as you can see, this is like a generalized form of what I had written before when I was expanding out the formula that was given by the theorem. So now, uh, this is this is in general. This is only when our yj is equal to 1, and everywhere else the output value or the second coordinate becomes 0. But then we don't really always deal with points which have some x comma 1, or points which are like x comma 0, right? Because our y coordinate can not just be this binary 0 or 1. It can range from positive, big huge positive values to huge negative values. So how do we account for that? Right now in our hands we have just f1, f2, f3, so on until fn. In our hands we just have these basic building blocks of polynomials which give the output value as 1 and the output value as 0 in every other x coordinate which is not this 1, 2, 3, etc. So here is where our linear algebra comes into the picture. So we'll be using these as our building blocks, and using the concept of linear combinations and basis vectors, that's what we'll be doing. So right, so we'll, before going on into that, we'll require some prerequisites. These are, we won't be going into too much detail, we'll just be using these 5 concepts. So one is a spanning set. Spanning set of vectors is nothing but a set of vectors that spans an entire vector space, and in specific over here we'll be using the polynomial space. Linearly independent vectors, a set of vectors is said to be linearly independent if there exists no non-trivial linear combination of the vectors that equals the zero vector, which means all the scalars that are used in the linear combination of these vectors, they must be 0. Only then will the linear combination evaluate to the zero vector. A minimal set, so a set in which no vector is linearly dependent on another vector from the set. So it should not be a linear combination of the rest of the vectors. That is known as a minimal set. So a basis, it's basically just a minimal spanning set of a vector space. It should be minimal, the set should be minimal, there must be no dependencies, and it should also span the entire vector space. Matlab, the linear combination of those vectors must give you every other vector in that vector space. And finally, we'll just be using this corollary. We won't be proving this because of lack of time, but it says that in an n-dimensional vector space, a set with n linearly independent vectors is a basis. And just as a small digression, we'll be using this lemma, which basically says the set f1, f2 till fn is a basis for R n minus 1 of x. So this set is the set of those polynomials that we saw before, right? So f1 is the polynomial where f1 of x1 will be equal to 1. Can you see this, or did the screen just go black? 1 second. Yeah. So yeah, sorry about that. But this is f1 is the polynomial where f1 of x1 will be 1. Its output value will be 1 when the input value is x1, and at any other input value, the output is 0. So that is this polynomial f1. Similarly for f2 and so on till fn. So the set of these polynomials, we are claiming that it becomes a basis for Rn minus 1 of x. This is nothing but the vector space, a polynomial vector space, where every polynomial in that vector space has a degree at most n minus 1, less than or equal to n minus 1. And Manogna will continue with the proof.
So how do we prove this lemma? So it's very simple. We already know that the polynomial space of degree n minus 1 or less than that is an n-dimensional vector space. It has a basis 1, x, x square, so on up to x power n minus 1. That is a standard basis we already know. And that also has n elements. So to find out another basis, it should have two major conditions that it should satisfy. That is, it should have n elements, which we already know it has. That is, f1, f2 till fn has n elements. And we should show that f1, f2 till fn, the set is linearly independent. This is, since we already know it has n elements, we just need to show that it is linearly independent. Considering it is not linearly independent, that is, it is linearly dependent, and proving this by contradiction, since we are considering f1, f2 till fn as to be linearly dependent, there must be scalars a1, a2 till an, where not all of them are 0. That is, we don't have trivial solutions for this equation a1, f1, a2, f2, so on up to a1, an, f1 is equal to 0. For this, we'll get non-trivial solution if it is linearly dependent. So in order to prove this, we have we have a1 f1 of x1. So we already have the data set x1 and all those data sets. So we just put in the value of x1 here, and we already know that f1 of x1 is 1, and all other data points the function will be 0. So plugging in those values to the first equation that we have, we find the value of a1 to be 0. With the similar argument, we can show that all the scalars a1, a2, so on up to an will be 0, which is a contradiction to our assumption that not all aj's are 0. So here we got to know that all the scalars are 0. If all the scalars are 0, that is a trivial solution. Therefore, f1, f2, so on up to fn are linearly independent. So this proves that f1, f2, so on up to fn is basis of the polynomial space with n minus 1 degree, and it, of course, if it's a basis, it spans it. It's a minimal spanning set. Thus, any function of the polynomial space with the degree n minus 1 can be written in the form of alpha 1 f1 plus alpha 2 f2, so on up to alpha n fn. We are just using alphas here so that it does not get confused with the notations a1 and an. They are different.
So this was a quick digression. Coming back to our original proof, so we know that our interpolating polynomial, the one that is required for us of degree at most n minus 1, which passes through those n data points, right, that we have, that is also a member of this very same set, of this set R n minus 1 of x, right? Since it belongs to that, it can also be written in this form, right? So in particular, we can write it in that form, and the same polynomial should also satisfy these points x1, y1 till xn, yn. And all that's left for us is to find out what these scalars are, alpha 1, alpha 2 till alpha n. And how do we do that? We again use the data set that's available with us. We plug in x1 till xn consecutively and see that and equate it to y1 till yn, right? So here we are taking the first condition, f of x1 should be equal to y1. Plugging it in, here we plugged in x1, right? And as a similar argument as before, we see that only this part evaluates to 1, and every other polynomial, f2 till fn, all of that evaluates to 0, because they all vanish at any other point that's not the subscript value. So then we are left with alpha 1 should be equal to y1. And then we use the same argument, and we get that alpha j should be equal to yj, where j ranges from 1 to n. Now substituting it back into our this very general form, because we got alpha 1 to alpha n, we get that f of x, which is our interpolating polynomial, should be equal to y1 into f1 plus y2 into f2 till yn into fn. Here, please don't be confused. Here, yn is when we are referring to the output values. It is a single value. f1 is the polynomial, right, which evaluates to 1 at x1 and vanishes at every other point. So this might look a bit different from what we had seen before, but then if we expand it out, we'll arrive at the same, we'll come to the same equation, right? So as we saw before, we had these yj's outside, right? So that's there, and every yj was accompanied by a pretty longish looking equation, which looked of this sort, no? X minus x1 into x minus so the first, let me just erase this. So the first term will look like, yeah, so the first term will look like this, the second term will look like this, so on, right? So here we have the yj's on the outside, and this entire equation is nothing but f1. This entire equation is nothing but f2. So how do we know that it is f1 and f2? Because if we substitute the points here, if we substitute the points x1, y1, we'll get y1. So say we substitute x1 over here, x1 over here, so on. All of these points, all of these terms will just evaluate to 0, because it's f2 of x1, right? Fn of x1. So, and then this will be left with is y1 into 1. So this y1 into 1 should be equal to f of x1, and since it is the interpolating polynomial on our right hand side, that should be equal to our y1. So yeah, from both ends, if we see, we've gotten our interpolating polynomial. And there are also a few things to keep in mind. The theorem said that, there's also uniqueness property attached to it, that the polynomial that we do get, it is a single unique polynomial of degree at most n minus 1, which passes through the given endpoints. The uniqueness property we won't be proving right now, again because of time constraints. And there are also infinitely many ways to interpolate using complicated polynomials. So as we saw in our example, if we had 2 points and we could pass a polynomial of degree 1 through those points, but we could also pass a polynomial of degree 2. And how many of degree 2? Infinitely many, because one could look like this, one could look like this, etc. Right? So yeah, that's what this point is trying to say. And why are we able to do this? Because every degree that you add to the polynomial, it adds one more degree of freedom. It adds one more way of how you could manipulate that polynomial. Yeah. So we have proved our theorem, and we've come to the end. These are the resources that we had to go through, and thank you.
Thank you for your presentation. So any questions, if you have, you may ask them.
Yeah, Megha and Manogna.
Yeah.
Yes.
Yeah. So, like, say if some points are on a straight line, say 3 or 4 points are on a straight line, then like, how, is it good to approximate that with Lagrange methods? This Lagrange interpolation.
Just to make sure that I'm getting a question right, you said that if we have 3 points
Mm-hmm.
on a line on a straight line,
Yeah.
so you're saying we could get the equation of that straight line using the Lagrange's interpolation.
Yeah. No, I am. What I'm saying is, you have 3 points on a straight line. Then is it good to approximate the curve using Lagrange polynomial, Lagrange interpolation?
Well, technically, I don't think you would even need all the 3 points using, because the statement says that you can just use n minus 1 points. So, you can use those 2 points to find the uh, equation of that line. And that one extra point would be redundant.
Yeah. So, my point was, it's better to in those cases, it's better to use straight line, those things, because that is visible. No?
Yeah. And I think this
Easier, but then you can use Lagrange's, but then it's easier if you use the straight line equation because you already know that the points are collinear or something.
Yeah. Correct. Okay.
any other doubts?
Okay, so let us again thank our speaker.